An earthquake begins deep beneath Earth's surface. Within seconds, enormous amounts of energy travel through rock, oceans, and the atmosphere itself. But some earthquakes do something even more extraordinary. They send energy upward, through the atmosphere, all the way to the edge of space. High above Earth, invisible disturbances begin to appear inside the ionosphere, a vast electrified region filled with plasma and charged particles. Satellites can detect them. GPS systems can observe them. The atmosphere itself begins to move. But how can violent motion deep underground affect the upper atmosphere hundreds of kilometers above Earth? And how do earthquakes disturb the boundary between Earth and space? When most people think about earthquakes, they think about shaking ground, collapsing buildings, or tsunamis. But earthquakes are also enormous atmospheric events. Large earthquakes release tremendous energy into Earth's crust. Some of this energy propagates outward as seismic surface waves. As these waves move across Earth's surface, they can push upward into the atmosphere itself. The atmosphere responds by generating powerful atmospheric waves. These include acoustic waves, atmospheric gravity waves, and complex disturbances capable of traveling upward through multiple atmospheric layers. The atmosphere is not isolated from Earth below it. Earth, atmosphere, and near-Earth space are physically connected systems. And during major earthquakes, that connection becomes dramatically visible. As the initial shock waves from the earthquake radiate outward, they don't just travel through the ground. The immense vertical displacement of the Earth's surface acts like a colossal piston, pushing against the lowest layer of the atmosphere. This initial push creates a ripple, a pressure wave that begins a long, silent journey upward. As these atmospheric waves rise, something remarkable begins to happen. To understand it, we have to consider the fundamental nature of our planet's atmosphere. From the dense air we breathe at sea level to the near vacuum of space, Earth's atmosphere becomes progressively thinner with altitude. The air molecules become more and more sparse. For an upward propagating wave, this change in density is crucial. The wave carries a certain amount of energy. As it ascends into regions with less and less air to move, that same amount of energy displaces the few remaining particles more dramatically. To conserve its energy, the wave must grow in amplitude. What began as a subtle, imperceptible pressure fluctuation near the ground can amplify into a vast, powerful oscillation hundreds of kilometers above. After traveling for minutes, some of these amplified disturbances eventually reach the ionosphere, a vast, electrically charged region of plasma extending from about 80 kilometers up to 1,000 kilometers above the Earth. This isn't a layer you can see or touch in the conventional sense. It's a dynamic environment created and sustained by the sun. High-energy solar radiation, particularly ultraviolet and X-rays, streams into our upper atmosphere, striking neutral atoms and molecules and knocking electrons free. This process, called ionization, creates a sea of electrically charged particles, ions and electrons, intermingled with the neutral upper atmosphere. This tenuous, electrified shell is invisible to us, yet it is deeply integrated into the technological fabric of our modern world. The ionosphere plays a critical role in long-distance radio communication, bending signals back toward Earth to allow them to travel beyond the horizon. The accuracy of GPS and other global navigation satellite systems, whose signals must pass through it. The reliability of all satellite signals that connect our planet. And it is a key medium for complex space weather interactions with Earth's magnetic field. When the powerful, amplified atmospheric waves generated by an earthquake reach these heights, they don't just pass through. They physically push and pull on the ionized gas, disturbing the delicate balance of the ionospheric plasma itself. Using networks of ground-based receivers and satellite measurements, scientists have observed the direct consequences of this interaction. They see traveling ionospheric disturbances, or TIDs, ripples in the plasma that spread outward from the epicenter, mirroring the seismic waves below. Significant plasma density variations, as the atmospheric waves compress and rarefy the charged particles, and large-scale, coherent wave-like structures moving through the upper atmosphere for hours after major earthquakes. The connection is undeniable. Invisible waves, born from the violent movement of rock deep within the Earth, ascend through the air and begin disturbing the very edge of space above. To observe these subtle, high-altitude disturbances, scientists rely on a technology that has become an invisible, yet essential, part of our modern world, the Global Navigation Satellite System, or GNSS. While we know its most famous component is GPS, this global network is far more than just a tool for navigation. It is a powerful scientific instrument for monitoring our planet from space. Every signal transmitted between these satellites and the countless receivers on Earth must travel through the ionosphere, a vast region of the upper atmosphere, beginning around 80 kilometers up, where solar radiation creates a sea of electrically charged particles, or plasma. For everyday GPS users, the ionosphere is a source of error that our devices must correct for. But for scientists, this interaction is a source of invaluable data. When the ionospheric plasma is disturbed, the properties of the radio signals passing through it also change. The speed of the signal is slightly altered, causing it to arrive at the receiver a tiny fraction of a second earlier or later than expected. These minute variations are imperceptible for navigation, but they are precisely what scientists are looking for. Scientists quantify these variations using a measurement known as total electron content, or TEC. It represents the total number of electrons present in a column between the satellite and the receiver. By continuously monitoring TEC from thousands of ground stations around the world, researchers can build a dynamic, global map of the ionosphere's state. Following major earthquakes, satellite observations have revealed astonishing phenomena. Immense wave-like disturbances in total electron content propagating through the ionosphere, often mirroring the events on the surface below. These ionospheric signatures are often detected just minutes after a large earthquake, as the initial, powerful ground shaking sends acoustic waves rocketing upward through the atmosphere at the speed of sound. They are also seen in the hours following a quake, generated by the tsunami itself. As the massive displacement of water pushes on the air above it, it creates atmospheric gravity waves that leave a clear, moving imprint in the ionosphere that travels at the same speed as the tsunami below, and they are observed as seismic surface waves ripple across continents, their passage across the landscape creating a corresponding disturbance that races through the plasma hundreds of kilometers overhead. These modern satellite systems provide undeniable proof of a deeply interconnected Earth system, allowing scientists to directly observe how immense energy from the solid Earth can couple into the atmosphere and ultimately into the electrified edge of space. In some cases, these disturbances spread across enormous regions of the upper atmosphere, traveling for thousands of kilometers and lasting for hours. Earthquakes, it turns out, do not only disturb the ground beneath our feet, they can also profoundly disturb the delicate fabric of space right above our heads. Tsunamis can also generate ionospheric disturbances. As tsunami waves move across the ocean, they push against the atmosphere above them. This generates atmospheric gravity waves capable of propagating upward into the ionosphere. Satellites have detected these disturbances after several major tsunami events. In some cases, ionospheric perturbations have been observed thousands of kilometers away from the original earthquake source. The atmosphere becomes a transmission pathway connecting oceans, earthquakes, atmospheric dynamics, plasma physics, and near-Earth space. The boundary between Earth and space is far more connected than most people realize. Earth is not an isolated world. It is a dynamic, interconnected system, a vibrant sphere of activity from its molten core to the very edge of space. We tend to perceive our planet as solid ground beneath our feet, a stable haven in the vastness of the cosmos. But this perception misses a profound truth. Our world is in constant, silent conversation with the space that surrounds it. Beneath us, powerful geological forces constantly reshape the planet. The slow, inexorable drift of tectonic plates, driven by the heat of the Earth's core, builds mountains and forges oceans. These are the same forces that, when suddenly released, generate the immense energy of an earthquake. And far above us, a different kind of power holds sway. Invisible plasma and charged particles, a constant stream from the sun, interact with Earth's protective magnetic environment. This is a realm of unseen energies, a delicate shield that makes life on the surface possible, yet it is far from static. Between these two domains, the solid Earth and the plasma of space, lies an atmosphere capable of transmitting energy from Earth's surface toward the void. It acts as a bridge, a medium through which the planet's internal convulsions can communicate with its upper atmospheric layers. For decades, this connection was only a theory. But now, our modern constellations of satellites have revealed that major earthquakes can, and do, disturb the ionosphere. They achieve this through complex atmospheric coupling processes, a chain reaction of physical phenomena, including atmospheric gravity waves, which carry the imprint of the ground shaking upwards like ripples in a pond, plasma disturbances, where the energy from these waves disrupts the delicate balance of charged particles in the ionosphere, and large-scale traveling ionospheric structures that can propagate for thousands of kilometers. These groundbreaking discoveries are fundamentally changing how scientists understand the dynamic, living connection between the solid Earth and near-Earth space. We are learning that events on the ground have echoes in the sky, that our planet is a single, unified system. So the next time you hear of the Earth shaking beneath the surface, remember, the disturbance may not stop at the ground. Its influence travels upward, a silent testament to the fact that some earthquakes can truly reach the very edge of space. If you enjoy exploring the hidden physics connecting Earth, atmosphere, space, and life, subscribe to 360 Science and Life with Dr. Curious for more cinematic Earth and space mysteries. What hidden Earth-space interaction should we explore next? And could modern technology help us better understand the invisible connection between earthquakes, the atmosphere, and near-Earth space?